Okay. So that we can now start talking about roll. This is where it gets a bit mathematical with some equations. Okay. So follow along. If you've got the notes, that's good, but don't worry too much. We'll work through it slowly. Okay, so when a vehicle rolls, there's two couples, two moments that cause it to roll. Okay. Assuming you've got a roll centre that's below the centre of gravity, there's two things that cause the vehicle to roll. The first is the fact you've got a centripetal reaction force being applied through the linkages to the body. Okay, centripetal reaction is obviously pointing out of the corner. Okay, or the reaction force. Centripetal force points towards the centre of the corner. Reaction obviously is in opposite direction. Okay, and the other thing that happens is the fact that the centre of gravity, by rolling, is actually going to induce more roll because it shifts outside of the line of the roll centre. Okay, so you've got these two roll moments that are causing the vehicle to roll out of the corner. Okay, what stops it rolling over? Well, you've got springs pushing the other way. Okay, these are being opposed by the moment being generated by suspension springs. Okay, now obviously those things need to be in balance. That total roll moment needs to be zero, and then you end up with a situation where the vehicle's rolling. The springs are operating in the opposite direction, giving you a constant roll arc. So if we separate this into three separate things, if we look at the linkage forces to the tyre, then you can draw a picture that looks a bit like this. So as I said, the linkage forces will act through the roll centre. Okay? So obviously in static situation, you've got W1 and W2 for both tyres, wheel 1 and wheel 2. There's going to be a force in a corner that can be generated out. And there's also, I guess, a tensile force, often compression, it's going to be a line joining the centre of the centre. So there's the problem. So quite clearly in a situation, W1 plus W2 equals W, okay? And then obviously these will balance each other out, giving you a lateral force being generated, shown here, which will be matched up on these two. You can work out what T1 and T2 are based upon those forces. So if you look at that picture, okay, I've got my dimensions up there. To the left, to the right is positive x, upwards is positive y, and the clockwise rotation is positive. Okay, so if we take Newton's second law at each of the wheel contact patches, we can work out what T1 and T2 are based upon those forces, F1. Okay, cosine beta. So if you look at this point here. Okay, like I said, we know we've got this situation. Okay, you look at that point there, you've got a force in this direction, and you've got T1 here. And this angle is beta 1. Okay. So if you do the sum of the forces in the x direction, you've got F1 plus T1 cosine beta 1. That equals 0. So T1 quite clearly is going to be minus F1 divided by cosine beta 1. Okay. And likewise over here, some of the forces in the x direction, F2 minus T2 cosine beta 2. So T2 is F2 and cosine beta 2. Okay. So that's where that comes from. Then once you've got those T forces, you can take those moments about the centre of gravity and substitute T1 and T2. That gives you a force FA. Okay, so moments around the centre of gravity, so you've got these forces being applied here. Okay, there's a distance here at A. Obviously, this so that there's a like I said, you can generate the loads there. Oops, the moments around there, and obviously they must equal to the that creates a moment around the centre of gravity of that load F, which is your mv squared upon r. Okay, lateral force. Because if you plug in into this equation, these values for T1, T2, put them into here, also the cosine beta term will cancel out. And then we'll basically F minus F1 and F2. Okay. So you have it together, F1 and F2 now equals F, which is your mv squared upon r, times by the distance A, which is the distance of the centre of the roll axis. Don't worry, I won't ask you to derive this equation in any assessment. Okay, it's not a thing, but it's need to understand where it comes from. Okay. Now, there's a little trick we have to play here because, like I said, I generated a moment around the centre of gravity. We don't want a moment about the centre of gravity. We want a moment about the roll axis, but it just so happens that it's the same thing. Okay, if you fix the centre of gravity and you apply a force at the roll centre, the thing is going to rotate anti-clockwise on this situation around the centre of gravity. So the centre of gravity and the force being applied at the roll centre rotates around the centre of gravity. Which just happens that that's equivalent to fixing the roll centre and then applying a force to the centre of gravity. It's the same motion of that distance A in a sense. And so we assume this equivalence, okay? And that gives us the roll moment generated by the linkage forces around the roll centre, which is what we're looking for. Because the vehicle rolls around the roll centre, not around the centre of gravity. And so we make that equivalence, and then we end up with the moment around the centre of gravity of the load is equal to the moment around the roll centre. Okay, so it's the same thing, which is minus Fa, which is what we worked out. So that's the moment around the roll centre associated with the load. The lateral load is minus F times by A. Okay, so that's the first one. Now, if we look at the vehicle as it rolls, okay, that centre of gravity is going to shift out of line with the roll centre. Okay, the roll centre, assuming in the centre of the car, as the vehicle rolls, the centre of gravity will roll outside, and that's going to generate an additional moment. Okay, we've got distance A there, we've got an angle theta, the roll angle, and you've got a right angle triangle going on here. Okay, so if you've got that's A, theta, W. Okay, you can end up working out what that weight is. You've got this distance here. That's the lateral shift. So that's obviously A sine theta times by W will be the moment being applied around the roll centre, which is at this point here. Taking moments about the roll centre, we've got the moment about the roll centre due to lateral shift equals minus W, because minus is pointing downwards, times by A sine of theta, which is that distance, that lateral shift. Okay. lateral shift is A sine theta. Okay, and you multiply by the weight, which is the force, you get the moment being generated. Okay. Now, we assume that the roll angles are quite small. Okay, and so we assume small angles, and if you assume small angles, the sine of theta is equal to theta. Okay, that works up to about 20 degrees. Okay, 10 to 20 degrees. We don't have roll angles in that actually. Okay, so that's a safe assumption. If you took 20 degrees, let's go for 10 degrees. I'll convert it to radians, so I multiply it by pi, I divide by 180, so it's 1.7. Is that right? No, that's not right. On the wrong way. 10 degrees. Okay, 0.17 radians, okay. If I take the sine of that, 0.17, okay, so the inverse sine and the sine of that angle, they're virtually the same thing. Okay? Inverse sine, sine. Okay? So that's why you can make that assumption up to 10 degrees. It's the same thing. Okay? So that's a safe assumption to make. So the total roll moment are those two moments added together. Okay? Like I said, there's the moment due to the load, moment due to lateral shift. You add them together, you get the total moment being applied about the roll centre. It's applied to the centre of gravity. Okay? So we've got minus Fa and we've got minus WA times by theta. Okay? So that second term will depend upon the roll angle. Okay? The bigger the roll angle, the more that first will apply. Now, like I said, this is where it gets a bit more complicated. It's shared between the front and rear axles. This is about working out what A is, based upon that roll axis line. So you've got the ground, you've got this distance here, centre of gravity. That distance is A. This distance here was HF, HR. This distance is H. So you've got a distance here of AF and AR. Okay. So you can work out the distance of A from geometry. In fact, I think I've got a file on Blackboard that helps explain that. Blackboard. If it loads. It's taking its sweet time, isn't it? Well, that's why. But like I said, this actually works out analytically. So in reality, the lateral force is shared between the front and rear axles. Okay, so the total roll moment is you've got the front force, lateral force times by that AF. You've got the rear forces times by AR, and then obviously the same for that lateral shift force. Okay, and if you simplify things out, okay, you can actually work out so AF and AR as we saw before. So you could write it out like that, that's the lateral force. You go through the motions, you can actually end up solving, combine them together. There we go, that's one. So that's so basically that value A, okay, is this, basically that goes to find that value for A. So you remember there was F minus FA, well there's your F, okay, times by A, which is here, okay, plus WA, that's what all that's derived. So like I said, on Blackboard I've got a picture of how you do that. Let me see if I Is it loaded yet? Look. It's getting there, slowly but surely. Oh yeah, look, here we are. So they go to this module, Motorsport Performance. Calculation of A by geometry. You going there? Okay, so that's the picture on the side of the car. Okay. There's your centre of gravity. This is your roll axis. Okay. There's your HF and HR. Okay, so you can work out F and L. And you've got a couple of triangles here. Okay. There's this red triangle, which is the distance. Okay. And you've got a green triangle. So you've got length for the green triangle. That's going to be AF minus AR. That distance minus that distance. Okay. And there's another triangle here, which is distance of C. Okay. And then this distance is AF minus A. These are similar triangles. And so if you put the one side over this side, they should be the same ratio. There's obviously here, we know what AF and A are, we know what C and L are, we can work on all these. So you end up working out A is AF D plus ALC divided by L. Okay? So like I said, you can work it out graphically or you can work it out analytically. You just need to remember it like this. Okay? So there it is, AFD plus ARC over L is your value of A. Multiply that through, you end up getting the moment. Now, that moment needs to be opposed by the spring forces to stop the vehicle rolling over completely, okay? And so we end up working out what these spring forces are. So as the vehicle rolls round, okay, obviously one side is going to extend, the other side is going to compress. Assuming you've got a constant spring rate, okay, you can go through the geometry, okay, if you work it out, the extension compression is that T over 2 times by the sine of the angle, okay, because you've got the track width here. So that's T over 2. You've got this distance here, which is the distance that's going to compress or extend. Okay, so there's your extension and compression forces. Again, assuming small angles, you replace sine of theta by theta. Okay. The extension times by the spring rate will be the force, okay? But obviously it's there are two of them because there's one on both sides. Okay, so you've got your K times by X, okay, times by the, because we want to work out the moment, so you've got okay, Kx is your force. Okay, so there's the extension, times by K will be the force, times by the lever arm, gives you a moment, and there's two of them on each side. So you have K T squared. The total spring moment. But that's for one axle. Obviously there's springs in the front and the back. So you need to put both axles in there. The spring rates aren't necessarily the same. So you can separate it to Kf and Kr. T squared upon 2, you add them together and multiply by theta will give you the moment about the roll centre of the springs. Okay? Steady state roll, those two moments, the one from the load and the lateral force and the springs, you're going to add them together. Now, we know everything in here. We know M, V squared, R, W, F, AFD, ARC, and over L, we know those. We've got KF on the track, KR on the track. The unknown is theta. But what you can do is, if you go through the motions, it's laborious algebra, but you can get theta on its own. And if you get theta on its own, you end up with this equation. So mv squared times by A, which is AFD, plus ALC over L, okay, divided by R, mv squared divided by 4. That's your spring force, or your roll stiffness in a sense, okay, and then subtracted on W divided by A, which is So once you've got those bits of data, you can find the roll angle, steady state roll angle. Okay, so there are relationships between the roll angle theta various times, and some of these are self-explanatory. Clearly, theta is directly proportional to the natural acceleration, v squared upon r. Okay, that shouldn't be there. Okay, v squared upon r, which makes sense. Okay, the higher the lateral acceleration, the more the roll angle. And you can see quite clearly that that is in here. V squared upon r. There's your lateral acceleration. The roll angle is directly proportional to the roll centre height relative to the centre of gravity. Okay, and that's the AFD plus ARC upon L terms. Okay, so that's in here. In two places, it's there. Okay, it's also down here. And you think, well, hold on, it's in the denominator. Surely that will have an impact. But look, it reduces the denominator. Okay, there's a minus sign. Okay, so that reduces the total value in the denominator. Okay, so again, directly proportional. The roll angle is inversely proportional to the roll stiffness. Okay, so you've got the roll stiffness there with the K terms. Okay, here if you've got a car with a lot of roll stiffness, K-sprung tire increases the K terms in the denominator, which increases the denominator term, which increases the roll angle, that decreases the roll angle. Okay. It's also inversely proportional to the track T squared. Okay, because there's two T squared terms in the thing, and if you reduce the track, you increase your roll angle. There they are. T squared terms. So if those values go up, then the value in the denominator goes down. If those values go up, the value in the denominator goes up, which means the value of the roll angle goes down. So wide track will give you a reduced roll angle. Okay. A steady state. So that's how that works. That equation works. So here you go. Car's got the following suspension and body parameters. So there's your mass, your track, your wheelbase, your dimension C, centre of gravity, height. I've given you the height of the roll centres at the front and the back. I've given you the wheel rates at the front and the back. And the vehicle's travelling at 25 metres per second around a corner of radius 140 metres. Work out what the body roll is in this condition. So I'll give you a few minutes to work it out, and then I'll go through a sample solution. If you've got the notes, then there's a space in the notes, but if you haven't got notes, then do you want a piece of paper? Yes.